Every time a digital sensor captures an image, physical limitations degrade the signal. Lenses diffract light, and electrical resistance inside the camera hardware generates random interference. What begins as a perfectly crisp microscopic view is rapidly obscured. Optical blur distorts the physical boundaries, while sensor noise covers the remaining data. This equation models that physical degradation in continuous space. To reverse the damage, we must first define the variables within this process. The variable f of xy represents our target, the original, uncorrupted image signal as it existed before hitting the camera lens. This is acted upon by h of xy via the convolution operator, a mathematical representation of the specific blur unique to the imaging system. Finally, the system adds n of xy, accounting for the random electrical noise generated by the sensor. While this continuous 2D model accurately describes physics, a computer cannot calculate infinite spatial points. To restore the image, we must translate these relationships into a finite language machines can process. We do that by shifting to discrete linear algebra. This formulation represents the same physical degradation, but as a strict matrix equation. In this version, our original image f is no longer a two-dimensional continuous grid. Matrix math requires us to convert the image into a single column vector. The continuous blur has also been replaced by H, the transformation matrix serving as the engine for the entire computation. This makes image restoration a matrix construction problem. Successfully recovering the original image depends on structuring the degradation matrix to mirror real-world blur. To see how a two-dimensional blur functions inside a one-dimensional math equation, we can look at a discrete, microscopic spatial example and track the pixel data from first principles. This diagram represents a minimal 3x3 pixel grid. We will use this as our uncorrupted image f. Right next to it is our degradation function h, operating as a 2x2 convolution kernel. Because spatial location dictates the math, we indexed every pixel intensity by its row and column, from f11 in the top left down to f33 in the bottom right. In standard 2D convolution, that 2x2 kernel would physically slide across the 3x3 grid, horizontally and vertically, blending adjacent pixels together to simulate optical blurring. However, standard convolution relies on 2D adjacency, while matrix algebra strictly requires one-dimensional vectors. This dimensional mismatch forces us to dismantle the 2D spatial structure of the image before any restorative calculations can occur. The protocol used to convert spatial grids into linear data is called lexicographic ordering. The first horizontal row of image data, pixels f11 through f13, detaches and rotates 90 degrees to form the start of a vertical column vector. The second row extracts and stacks directly underneath the first. Once the third row follows, we have a single 9x1 column vector. This creates a mathematical distortion. Notice that f13 and f21 are now adjacent in the vector, even though they were separated on different rows in the original 2D image. If we pass our 2x2 kernel over the 3x3 grid without adding padding, we get a smaller 2x2 output grid, G. Applying the same lexicographic ordering to this output grid unrolls it into a 4x1 vertical column vector. Both the input and the output models are now strictly aligned to one-dimensional constraints. By flattening the 2D relationships into a 1D sequence, we transfer the burden of spatial awareness entirely onto the internal architecture of the transformation matrix. We must now define the operator mapping the 9-element input vector to the 4-element output vector. Based on matrix multiplication rules, to transform a 9x1 vector into a 4x1 vector, the degradation matrix H must be 4 rows by 9 columns. When we populate the matrix with the kernel weights, the spatial relationships are preserved using specific weights and strategically placed zeros. Tracing the first row shows how the zeros act as spacers. That highlighted 0 ensures the calculation skips pixel f13, mirroring the horizontal boundary of the original image. In the second row, the weights shift one position to the right. This shift mathematically replicates the kernel sliding across the image plane. This architectural pattern, active weights surrounded by zeros, is a block diagonal structure. This structure encodes 2D spatial convolution boundaries into a 1D space, providing a blueprint for the restorative computation. Our ultimate objective is unconstrained restoration, executed entirely in the spatial domain. We have our model, G equals HF plus N. We know the degraded observation, G, and the matrix, H. We need to find the target unknown, F. Pure algebra suggests a simple solution. Isolate F by multiplying both sides by the inverse of H. In the presence of real-world noise, however, direct inversion is unusable. Mathematically, transformation matrices are frequently singular, meaning they physically lack an inverse. Furthermore, these matrices often have poor condition numbers. This makes the system mathematically unstable, where a small change in input leads to massive fluctuations in the output. Multiplying an unstable inverse against the unmeasured noise vector exponentially amplifies high-frequency artifacts, which destroys the image data. Because of this instability, we must abandon pure algebraic isolation and pivot toward probabilistic optimization. Instead of solving for F directly, we set up a minimization objective. We use the mean square error, or MSE, cost function. The goal is to find an estimated image that minimizes the squared distance between our model and the actual degraded observation. To prepare for the derivation, we convert the squared L2 norm into explicit vector transpose notation. We then expand the binomial expression into its 4 constituent terms. Combining the identical scalar terms gives us the final expansion of the cost function. To find the minimum, we calculate the gradient and set it strictly to 0. Rearranging the terms establishes the equilibrium known as the normal equations. By applying the pseudo-inverse to isolate f, we arrive at the ultimate least squares spatial solution. Optimizing for minimal error bypasses the instability of direct matrix inversion. This provides a robust blueprint capable of suppressing noise while recovering the sharp features of the original image.
In classic signal processing and early neural network filtering, the default approach to cleaning up data is to minimize the error freely to fit the observed data as closely as possible. But on severely degraded data, that logic collapses. Attempting a perfect match to imperfect sensor readings causes the math to become unstable, fracturing the signal into jagged, violently oscillating spikes. To fix this, we move from free minimization to a conditional approach. We require the algorithm to find a function that fits the data while simultaneously satisfying a specific structural rule. This equation formalizes that requirement. We find the minimum of our objective, where G is our observed data, H is the system matrix causing the degradation, and F is the target function we want to restore. The first block here is the data fidelity term, measuring how closely our estimated solution matches physical observations. But it is now bound by C of F, acting as a mandatory mathematical boundary restricting the optimization landscape. By setting this boundary, we prevent the model from creating extreme noise just to hit a zero-error fit. It ensures the resulting inversion remains mathematically stable. We see the most common expression of this constraint here, bounding the L2 norm of an operation. We restrict the target F inside a strict geometric boundary. The L is a new matrix operator applied directly to our target function. The threshold epsilon defines the absolute radius of our geometry. It dictates the maximum allowable limit for a specific physical property of that signal. Look at this erratic 1D data. When we define the operator L in practice, such as by applying a derivative or a discrete Laplacian matrix to this data, it targets specific behaviors. By bounding a Laplacian, we enforce spatial smoothness. The math penalizes extreme changes in the slope. If the algorithm attempts to generate high-frequency noise, the L operator amplifies those jumps, causing a violation of the strict epsilon threshold. The L operator acts as a physical filter. It forces continuity into the system and prevents erratic oscillations in the final solution. Computationally, trying to solve an optimization sequence while checking against a hard geometric boundary is exceptionally difficult. This transition shows how we bypass that problem. By using Lagrange multipliers, we convert the rigidly constrained problem into a continuous, unconstrained one. The scalar variable lambda effectively absorbs the hard boundary and transforms it into a direct mathematical penalty. This gives us our unified objective function, known as Tikhonov Regularization. The first component is the data fidelity term. It tracks the residual error between our model and the sensors. The second component is the regularization term, which measures how much the solution violates our smoothness rule. Lambda sits between them as the critical trade-off parameter, balancing these two competing objectives. Setting lambda too high forces the algorithm to prioritize absolute smoothness, which can blur out real, accurate details in the data. Setting lambda too low does the reverse. It over-prioritizes pure data fitting, risking a return to unstable, noisy inversions. This single convex equation provides the framework for most modern linear restoration. It creates a solvable path to finding the exact compromise between sensor reality and physical constraints. To find the mathematical minimum of this objective, we expand the L2 norms into quadratic matrix forms, starting with the data fidelity term. We are applying the rule that the squared L2 norm of a vector is simply its transpose multiplied by itself. We apply that same vector norm rule to the second half of our objective function, the regularization term. Notice the matrix mechanic. Applying a transpose to a matrix vector product reverses the order of the terms. Returning to the first term, we fully distribute the binomial using standard cross multiplication. The first multiplication generates the scalar G transpose G. The cross multiplications generate the two middle terms, negative G transpose HF and negative F transpose H transpose G. The final multiplication results in the quadratic target term, positive F transpose HF. We can isolate those two middle cross terms and simplify them algebraically. Because both G and HF are vectors, taking their dot product results in a single scalar value. Since the transpose of any scalar equals itself, these two terms represent the exact same mathematical value. We combine these identical elements into the single simplified term, negative 2 F transpose H transpose G. When we reassemble the components, we get the fully expanded objective function, J of F. Look at the resulting structure. The target variable F appears linearly in the middle and quadratically at the end, while the first term relies entirely on constants. We have unpacked a pure distance metric into a solvable convex polynomial. Because it is convex, it contains a single, definitive global minimum. We reach the final mathematical step to find that minimum, applying the gradient operator with respect to our variable f. The constant data term differentiates to 0, while the linear term drops its f transpose to become -2 h transpose g. The quadratic terms differentiate like x squared in standard calculus, bringing down a multiplier of 2. The exact minimum of a convex function is located where its gradient equals the 0 vector. We set the expression to 0 and divide by 2 to strip the coefficients. We finish the algebraic cleanup by shifting the constant observation data to the right and factoring out the common vector f on the left. By isolating the structural system matrices together on one side, we have set up the final algorithmic inversion. Finally, we invert the combined system matrix and multiply it to the right side to explicitly solve for f. This is the constrained restoration solution. H transpose H comes from the degraded observation. H transpose G represents the raw observed data back projected into the target space. The addition of L transpose L represents the mathematical enforcement of the physical constraint, scaled by lambda. This single equation represents a closed-form harmony, resolving the conflict between trusting flawed sensors and requiring a physically meaningful result. When we compare this to the unconstrained least square solution, the difference is concentrated entirely inside the inversion bracket. If the standard degradation matrix is ill-conditioned, meaning nearly singular, calculating its inverse is wildly unstable. That instability is what triggers the noise amplification seen earlier. The addition of the lambda L transpose L term alters the geometry of the matrix, shifting its eigenvalues to stabilize the inversion process. The constraint dictates the final form. Laplacians enforce smoothness. Total variation preserves sharp edges. Sparsity constraints enable compressive sensing to isolate distinct signals. Constrained restoration provides the framework that stops algorithms from hallucinating noise, forcing the final solution to remain consistent with the actual signal structure.
The core computational objective in image restoration is extracting a true, original signal from a heavily distorted observation. We are given a degraded output, and we have to calculate our way backward, snapping it back into focus. Historically, mathematicians approached this problem using classical paradigms: inverse filtering, least squares Wiener filtering, and constrained regularization. The philosophical differences between these methods are stark. Direct methods attempt to rigidly calculate an exact inverse of the physical blur matrix, while statistical methods attempt to minimize the overall estimation error across the entire image. Identifying the structural flaws in these classical models explains the architectural choices made in modern deep learning. This equation defines inverse filtering in the frequency domain. It is the most direct approach, taking the observed data, G, and dividing it by the known physical blur, H. The spatial matrix equivalent of this division involves calculating the pseudo-inverse to isolate the target signal. However, this equation assumes a perfect theoretical environment. It completely ignores the existence of system noise generated by camera sensors or the environment. In ill-conditioned systems, values in the degradation matrix approach 0. Because this matrix is in the denominator, dividing by these near-zero values triggers an exponential explosion in the resulting signal amplitude. Pure mathematical inversion is a rigid calculation. The moment observational data deviates from perfection, the operation amplifies high-frequency noise until the image is unrecognizable. To counter this noise amplification, engineers moved from direct division to statistical error minimization using least squares Wiener filtering. The objective shifts to minimizing the expected value of the L2 norm between the true image and the computational estimate. The Wiener equation introduces a specific noise-to-signal ratio to the denominator as a stabilizing mechanism. This ratio functions as a mathematical floor. Even if the degradation drops to 0, the denominator cannot zero out, preventing the amplitude explosion seen in pure inversion. Wiener filtering achieves stability by trading the goal of perfect inversion for a statistically derived best estimate. Constrained filtering creates a dual objective system, fitting the observed data while forcing the output to conform to a structural prior, such as expected smoothness. This objective function minimizes the residual error while adding a lambda penalty term to enforce that structural prior. Tikhonov regularization alters the spatial pseudo-inverse by injecting a structural matrix guarantee directly into the calculation. While stable, calculating the absolute inverse of these combined matrices is computationally exhaustive for high-resolution sensor arrays. These one-shot algebraic solutions are also non-adaptive, meaning they cannot adjust to localized anomalies within the data. Because these direct calculations remain static across the whole image, engineering practices shifted toward more flexible, iterative frameworks. To improve flexibility, the restoration problem can be restructured as an optimization sequence rather than a single matrix inversion. The goal is to incrementally shrink the residual error, the difference between the observation and our estimate, through step-by-step updates. In high-dimensional data, conflicting local points often cause a single global calculation to fail. Continuous iterative cycles allow the algorithm to adjust its trajectory, diffusing these local instabilities over time. This incremental approach provides the opportunity to correct errors that would otherwise lead to the rigid failure states of global inversion. Gradient descent serves as the foundational mathematical engine driving all of these sequential trajectory corrections downward toward the optimal solution. The baseline logic is simple.
The new estimate equals the current estimate minus a scaled correction term. The gradient of the objective cost function, j, dictates the direction of the steepest increase in error, which we move against to find the minimum. The alpha term defines the step size, dictating how aggressively the algorithm updates its belief at each iteration. Expanding this reveals the operational residual error, the difference between the sensor data and our blurred estimate. The adjoint operator, H transpose, maps this error from the image space back into the underlying parameter space. By applying this adjoint matrix, every update is targeted to the geometric reality of the original degradation. During execution, the algorithm blurs the current estimate to compute its error against the raw sensor data. Large initial deviations result in aggressive mathematical corrections through the adjoint matrix. As the residual error shrinks, the correction term zeroes out, allowing the recovered output to stabilize. We can integrate structural constraints by taking the derivative of the regularized objective function, which appends a penalty term to each update. This penalty acts as a structural anchor, pulling the calculation toward a physically realistic result at every step. Up to this point, these models assume the degradation matrix is known, but what if the physical distortion is completely unknown? We can instead use paired datasets containing heavily degraded inputs and their corresponding clean ground truth targets. Because convolution is cumulative, we stop solving for image variables and begin solving for an unknown filter weight matrix. The goal becomes finding the optimal computational weights that map the degraded signal back to the ground truth. Training a weight matrix against paired data, rather than using known physical parameters, is the baseline of supervised machine learning. We can computationally solve this by applying the constrained gradient descent framework directly to the new weight-finding parameters. The final update equation shows the new weights are equal to the old weights, plus the scaled gradient of the error, minus the structural penalty. This adaptive mathematical filtering equation provides the operational mechanism for training. The limitations of one-shot inversion made the adoption of adaptive, iterative loops a practical necessity for processing complex visual data. Deep learning architectures apply adaptive signal processing at a massive scale, refining weights using the iterative logic developed for these early filters.
Relied on a strict mathematical assumption. We had to know the exact degradation operator, represented as H, that caused the damage. That assumption breaks down when the distortion is completely unknown. We often find ourselves with a degraded image and access to the clean ground truth original, but absolutely no mathematical blueprint of how the corruption occurred. To solve this, we set up a mathematical objective, minimizing the squared Al2 norm of the residual error. F is our pristine target image, G is operational input data, leaving W as the optimal filter weights to discover. Because convolution is cumulative, we bypass the unknown distortion entirely. The task simply becomes a weight-finding optimization problem. We formalize this search by defining a cost function, J of W. This gives the system a stable mathematical landscape to navigate while hunting for optimal weights. We also add a regularization penalty term to the equation. This addition, lambda times the squared norm of LW, restricts the weights and prevents the system from overfitting to random noise in the signal. This expanded cost function defines the complete linear optimization landscape. Long before modern machine learning, this equation explicitly dictated exactly what our mathematical models had to solve. We have our cost function, J of W. The mechanical problem now is figuring out how to actually calculate its absolute minimum value. We find that minimum using an iterative engine, gradient descent. The next state of our weights equals the current state, minus a step. This step is scaled by a learning rate, alpha, moving along the gradient path, nabla j. When we apply that gradient operator directly to our previous cost function, we get this expanded update rule. Look closely at the resulting math. The update relies entirely on a linear combination of matrix transposes, G transpose and L transpose. This linear combination executes basic signal mapping. However, it cannot account for the complex, nonlinear relationships found in natural data. Resolving modern, intricate signal distortions requires abandoning this strict linear framework entirely. To process complex reality, the mathematical architecture shifts its structural inspiration toward biological neural dynamics. Instead of executing flat, global matrix operations across an entire signal at once, the system is rebuilt into a localized, node-based processing architecture. This schematic details the biological model's first half. Data extraction begins by pulling a localized patch from the input image. That two-dimensional patch is flattened into a column vector, acting as the initial stimulus. During summation, every pixel value is multiplied by a specific weight. Mathematically, the output generated by this summation block is identical to the GWK term from the classical linear model we established earlier. If the architectural evolution stops at this summation block, the system possesses no added expressive power. It is still functioning as a classical linear filter. A limitation is broken by a single critical component, the nonlinear activation function, labeled here as phi. By passing this summed data through functions like ReLU or Sigmoid, the model gains the ability to learn complex, abstract relationships. Structurally, this single function acts as a mathematical barrier. It prevents a multi-layer system from collapsing into a single redundant linear matrix operation. This has an immediate consequence on our optimization target. The new cost function must wrap the classical linear terms securely inside the nonlinear phi function. Consequently, the gradient must differentiate directly through that nonlinear phi layer during the update cycle. Calculating this gradient requires the calculus chain rule, which shifts the trajectory of the weight updates. Integrating the chain rule into the gradient update is the foundational mathematical DNA of all modern neural network training. A single nonlinear neuron still possesses capacity limits. To process massive, real-world datasets, the architecture has to scale. This diagram shows the structural solution for high-dimensional abstraction. The system scales horizontally and vertically, following a 3-2-1 hierarchy. Data moves from initial nodes through intermediate nodes to a single output. Every transition contains distinct weight matrices and a fresh nonlinear activation, phi. The output of layer 1 acts as the direct input to layer 2. The signal is continually wrapped in a sequence of activation functions as it travels forward. Despite this nested mathematical complexity, the ultimate objective remains identical to the linear model we started with: minimize the residual error against the target image. This introduces our final optimization challenge. We have to mathematically update the specific weights buried deep inside the very first layers of this massive structure. To do this, the gradient error signal must physically penetrate backward from the output, peeling through every outer layer until it reaches the start. Calculating the partial derivative for an internal layer demands an intensive application of the calculus chain rule. This recursive, multi-layered operation is backpropagation. That brings us to the finalized, generalized mathematical equation that defines the modern deep learning paradigm. We are minimizing the difference between the target, f, and the entire deep network function, n of g, subject to the system's weight constraints, c of w. Deep neural networks are the logical mathematical evolution of classical iterative filtering, deliberately engineered to map unknown signal distortions.